All right, guys, this is the last formal lecture video over chapter 10. It covers sections 7 through 9, and we're going to talk about how gases actually behave by introducing our more realistic kinetic molecular theory. We'll end this chapter by discussing how real gases behave using the van der Waals equation as well. Okay, so the kinetic molecular theory takes what we assume about PV equals nRT in the ideal gas law and says, okay, so what's actually happening at the molecular level? We're not just using observations of how pressures and volumes are related. We are, in fact, more importantly, looking at the behavior of the molecules themselves. Instead of just witnessing what they're doing, we're more looking at how they're actually behaving. So this guy is going to go through, and we're going to have what we call main tenets of this particular theory. The first one is that gases are going to be consisting of large numbers of molecules that are always moving in a random way. So they are not going to move in predictable paths. They have random motion. There's no way to predict their paths, and so on and so forth. The next tenet is that the combined volume of all the molecules is going to be nothing compared to the volume in which the gas is contained. So in other words, it doesn't matter if I've got 45 moles of H2O gas in this particular, let's say this is a 250 liter flask, okay? And then it doesn't matter if I have that or if I have this many moles in the exact same size flask. You will not notice the difference, is the theory. The combined volume of the individual gas particles is nothing compared to the huge volume in which it's being contained. Okay? Another thing we want to think about is the forces between our molecules. So in other words, an H2 molecule and an H2 molecule is kind of coming upon each other. The attractions and repulsions that those two molecules may feel won't matter. Again, because the container itself is so large, the molecules are so far apart, that those forces are not enough for us to even see any kind of an effect up close. Sorry. Okay. Another tenet is going to be that energy can be transferred during collisions, but overall, the average energy of those molecules will not change. If and only if the temperature stays the same. So if I'm holding a liter of gas at 25 degrees Celsius, once in a while, gases are going to hit each other. Okay, the particles are going to collide with each other. When they collide, there is a larger number of energy involved, right? A collision produces energy, but the overall energy of all of the gas particles moving around in the flask, when you add them together, the overall average kinetic energy will be completely unaffected by those individual collisions that may be occurring. It doesn't matter how many collisions occur, the overall average kinetic energy will stay the same, which means the temperature should also be staying the same if that's what we're saying. Okay? Another thing that you've seen before, and I know you already know, is that kinetic energy of anything is related and directly measured by temperature. So in other words, if we say that the gas molecules are being held at 0 degrees Celsius, the average kinetic energy of those molecules is going to have that particular temperature as well. So in other words, as temperature goes up, kinetic energy also goes up. As temperature goes down, kinetic energy goes down. All right, next topic is effusion. So this is a little bit different. You've heard the term diffusion before, but effusion is the gas version of a gas molecule that escapes through a tiny hole. When helium balloons deflate, it's because the helium escapes through tiny holes in the balloon. No material is completely solid as far as we're concerned, in that every type of material has holes in it, even on the microscopic level. At that microscopic level, when that gas can escape through those tiny holes, we call that particular process effusion. Again, over time, we see that both gases are going to effuse. Now, helium will go faster because helium is smaller, right? Smaller molecules can escape through the same size holes faster than larger molecules like argon can. So, for a longer period of time, this argon will be contained compared to the helium. Diffusion, which you've seen before, is going to be how a substance spreads through a space. So how a single substance, think like sugar, can spread from one area to another. If you want to test this yourself and you are interested, you can add a sweet and low to your coffee without stirring it and see how long it takes for that sweet and low to make it up to the top of your coffee cup. Now, that being said, make sure you add it and then don't stir it or move it, because if you take that first sip, it doesn't taste very good. If you stir, it tends to taste better because that sugar is being dispersed. The process of the sugar moving on its own, which will occur over time, is what we call diffusion. All right, so Graham's law is a law that describes how the speed of two gases can be associated with each other. In other words, the speed of one gas versus the speed of another can be compared as to how fast the second gas is moving compared to the first. And last, of course, but not least, is how real gases behave. So the ideal gas equation really only works if we talk about gases behaving at high temperature and low pressure. Now, it just so happens that high temperature and low pressure is the atmosphere of the Earth. So, when we talk about gas, it makes sense that our observations, our ideal gas laws, and the things we've come across already all relate back to how they behave on the planet, because all of them were studied on our planet, right? Moving forward, though, if we were, say, doing this in a different type of pressure to atmosphere, on a different planet, on the sun, etc., gases behave very differently. And how they really behave is something that's been described using a couple of different methods. The same gas behaving at different temperatures can be described as to how it should behave, right? So relatively high temperatures, relatively low pressures. Low pressures are down here, sorry. And the temperatures all vary in this particular diagram, but under high pressure at different temperatures, you see that the gases all behave very differently. Their relations get kind of out of whack depending on where they're at. So again, we are here. These are our Earth observations. Everything else is kind of a simulated different type of pressure environment. Okay, those deviations from real behavior tend to also mess with the assumptions made in the KMT, or kinetic molecular theory. The negligible volume of gas molecules and no attractive forces all tend to break down the higher the pressure gets or the lower the temperature gets, because at lower temperature, things are moving slower. At lower temperature, we're also seeing that things collide more often. At the high pressure, again, same idea, more collisions are happening. And so a couple of the things that we tend to ignore under kinetic molecular theory become incorrect to assume. And we can correct for non-ideal behavior using what we call the van der Waals equation. It's a fancy looking equation, but it's the only equation in this particular section that takes the ideal gas equation and adjusts it so that you can actually identify information about the real gas behavior. And for the van der Waals equation, which is kind of scary looking and is up here at the top, it has new variables. Some of these variables are all the ones you've seen before. You still have temperature, again in Kelvin. You still have R, which is our 0.08206. You have moles. You have moles. You have moles. You've got volume a couple of times. You've got pressure. And then you have a couple of new things. The first is B and the second is A. A and B. A and B are what we call corrected versions or corrective factors. They are constants for different substances at any temperature. So in other words, if you're dealing with a carbon tetrachloride gas, A will always be 20.4, B will always be 0.1383. And so you would plug these in just like you would R to solve for whatever you're missing. So say you were trying to calculate a temperature, you would have to have everything else in order to calculate that temperature. Say you're trying to calculate a pressure, you would have to have access to moles, volume, A, B, and R and T in order to get that pressure value. From there, it's just manipulating the equation. Okay. All right, so that is the van der Waals equation. That's pretty much the major topic as far as math is concerned in this particular chapter. Probably the most tough one, but that's really all there is as far as the end of chapter 10 goes. All right. Have a great day.